Welcome to our notes and applications of area of oblique triangles. Students will be able to find area of geometric shapes by justifying what is the most appropriate formula based on what is known about special right triangles, right triangle trig, and area of oblique triangles as evidence. So here are the formulas to find the area of any triangle. There are three formulas. The first one is the one we are most familiar with. So the area of a triangle is 1/2 base times height. You can use it when you know the height and the base of the triangle. Formula 2 says the area of any triangle is 1/2 the product of the lengths of the two sides times the sine of their included angle. And that is the following three formulas depending on which sides you have and which angle you know about. So you can use it when you know two sides and the angle in between. So that means you know side, angle, side. This means a SAS case. Formula number 3 says that the law of cosines can be used to establish the following formula for the area of a triangle. This formula is called Heron's area formula. Given any triangle with side lengths A, B, and C, the area of the triangle is given by the following. So you can use this when you know all three sides, meaning you have the SSS case. So if you turn to the next page, we'll actually work out an example. Here's the verbal. A regular octagon is inscribed in a circle with a radius of 15 inches. And just to remind you, a regular polygon is a polygon that is equiangular, which means all the angles are the same, and equilateral, meaning all the sides have the same length. So the first thing I'm going to do is I'm going to understand the problem. So the best way to understand the problem is to draw a picture. So as we see, what it means to be inscribed means to be inside of something else. So the regular octagon is inside a circle where, the vertices are actually touching the circle. All right, so now what I'm going to try to do is, because we are in a trig unit, I want to try to find triangles in here. So I think it might be best to break up this octagon into triangles so I can use information I know, like the law of sines or the law of cosines, or which area formula I'm going to use, since I'm actually going to try to find the area of the octagon. That is my task as it is stated here. So if I break things up, I first need to identify where the center is. So I'm going to do my best to approximate it right here. Just, for diagram purposes, just know that you're trying to find the center. I'm going to call it C. And I'm going to draw lines from each vertex of the octagon to the center so I can see these triangles. Okay. Alright, so the one thing I can say about having a regular polygon and breaking it into triangles is that all of these triangles are congruent and they are all isosceles. So I'm going to call this A and this B. All of these triangles are going to be congruent. And I know them to be isosceles. So I know that that side length is going to equal that side length. And that makes sense because the radius of the circle is 15 inches. So this is going to be 15 inches. And this is also going to be 15 inches. That kind of makes sense. So also, if you remember anything about an isosceles triangle, you'll know that these two angles are going to be congruent. So I'm going to label them with the same angle notation or angle marks. Now, I think it's important that I find what this angle is because I can't find the other ones until I find that one. So I'm actually, for my plan and solve, I'm actually going to just draw that one triangle and try to figure out what I can do. So all I've done down here was just to recopy what I found, just one of these triangles down here in my plan and solve, just so I can just focus on this one triangle. So it seems like if I can find angle C, then I would have side angle side. And I think that's important. So I'm first going to plan. I'm going to find angle C, and I'm actually just going to go ahead and do that right here. In order to find angle C, since all of these triangles up here are all congruent, then all of these angles are going to be congruent. And what happens when you add up all of these angles? It will add up to 360 degrees. So what I want to do is I want to do 360 divided by the number of triangles that I have. So 360 divided by 8 is going to give me 45 degrees. So now that I know that this is 45 degrees, I'm actually going to draw that in here just to give me a reminder that I know that. So this means I have the SAS case. So I'm going to want to use, since I'm trying to find the area of the octagon, I want to use Formula 2 from the first page to find area of one triangle. And once I have the area of one triangle, I multiply area of one triangle by the number of triangles we actually have in the octagon, which is 8 by 8, because I have 8 triangles. So I'm actually going to combine steps 2 and 3 together when I actually solve this. So I'm solving this now. So the formula that I'm going to use, area of triangle, is going to be 1/2 AB times, that's a times right there. Hold on, let me just make that better. Or rather, let me just not do that at all. Okay. Times the sine of C. Now, I know that you guys are probably used to writing A for area, but I don't want to use A for area. I actually want to write out the word area because A right now is an angle. So I don't want to write A and then get myself confused. So I'm going to write out the word area, and I use a little subscript of a triangle to let you know that I'm only finding the area of one triangle there. And for the area of the octagon, now, I would probably draw an octagon, but I think that takes much more effort than to write out the word octagon. The area of the octagon is going to be 8 times the area of the triangle. So 8 times 1/2 AB sine of big C. I'm going to simplify this a little bit because why not? 8 times 1/2 is 4. Also, I know that A equals C. Not A equals C, A equals B, because it's an isosceles. So I can just go 4A squared times the sine of C, or you can leave it as A times B, that's fine. So now I'm just going to plug things in. 4 times 15 squared times sine of 45 degrees. Well, guess what? We already know what sine of 45 degrees is without a calculator, so let's first find the exact answer. When I plug this into my calculator, or the 15 squared times 4, I get 900. And then sine of 45 degrees is root 2 over 2. So if I simplify a little bit more, I get 450 times root 2 square inches. So that's the exact answer. But of course, to put this in, to give us a little bit more perspective, if I put that in a calculator and round to one decimal place, I get 636.4 square inches. And that is the area of the octagon.